Okay. Um, in this video, we're going to talk about the other way that they ask trapezoidal rule questions, and that's usually by giving you a table of values. So instead of actually figuring out for yourself what those outputs are that need to be plugged into the formula, they don't give you the function so that you can go chase after them. They give you a table of values. And I think the reason they do this is that oftentimes you don't have an equation when you're applying stuff like this in a scientific way. You've basically uh, gathered data, and you're basically using these tools to evaluate data that you've been given. And data shows up in a table like this. Well, this one seems rather straightforward, and on the AP exam it won't look like this. I mean, there won't be, four in a row, or estimate the left hand, estimate the right hand, estimate the midpoint, estimate the trapezoidal rule. You may be asked one or two of them, and they'll be in one part. But this is a worksheet that I sort of picked up online, and it's basically just a nice excuse to sort of walk through it. Now, if we're given a table of values, notice that this table has 7 columns. Well, if it has 7 columns, that defines 6 subintervals, right? Because the first subinterval runs from 0 to 20. The second subinterval runs from 20 to 40. The third, the fourth, the fifth, the sixth. Now notice down here on part C, it asks for 3 subintervals. Well, if you were asked for 3 subintervals, you would just skip over 20, 40, and 60. Okay, and so you have a choice when you're given 7. You either have 6 subintervals or you have 3 subintervals. Well, doing the left-hand Riemann sum would be easy enough. We can go ahead and do that. If we're looking for the left-hand Riemann sum, we need delta x, okay? Because remember, you're dealing with the area of rectangles on left-hand Riemann sum. And so you have 20, and then you just have to add up the first 6 of those the first 6 of those output values. 1.2, 2.8, 4.0, 4.7, 5.1, and 5.2. And of course you could do that by hand or plug it into your calculator. It really doesn't matter. The right-hand Riemann sum would be similar, except for you wouldn't use 1.2 to 5.2, you'd use 2.8 to 4.8. And so you have 2.8 plus 4.0 plus 4.7 plus 5.1 plus 5.2 plus 4.8. We're going to skip over C. That would be A and B. The trapezoidal approximation, remember, is going to be 10, okay, because it's going to be the delta x divided by 2. And then it would just be 1.2 plus 2 times 2.8 plus 2 times 4.0 plus 2 times 4.7 plus 2 times 5.1 plus 2 times 5.2 plus 4.8. Okay? Well, that's easy enough. Let's go ahead and look at those in terms of the numerics of it, okay? The first one is 1.2 plus 2.8 plus 4.0 plus 4.7 plus 5.1 plus 5.2, and then you just multiply that by 20, and therefore it winds up being 460. Okay, well, if you steal that right there, and you basically, I don't want to pedal over, so we'll subtract that first value, and then add the last value, and we'll multiply that by 20, that'd be 532. Now remember that I told you that the trapezoidal rule is the average of the left-hand and right-hand Riemann sum, so let's see whether that actually plays out, okay? So I have 1.2 plus 2 times 2.8 plus 2 times 4 plus 2 times 4.7 plus 2 times 5.1 plus 2 times 5.2 plus 4.8, and then of course we have to multiply it by 10, and lo and behold, we do actually get 496 as we predicted. Okay? And those output values came not from actually evaluating a function, but just picking the values out of the chart that's actually provided for you. Okay? Well, let's move on to another example. Let's move on to this one. Now, I'm going to give you a second, and then I'm going to ask you this question. What is different about this one as opposed to the previous one? Take a careful look. The difference is this has, well, the very first difference you'll notice is that it's got 4 subintervals instead of 6. Another thing is that these don't have uniform width. Do you see it? The first interval runs from 0 to 40. The second interval runs from 40 to 70, so that's 30 units wide. The next one runs from 70 to 90, that's 20 units, and then 90 to 100, that's 10 units. Well, is that going to mess us up? Well, formulaically a little bit, but as long as you understand how to deal with it, it shouldn't really be that big of a deal. Okay? Now notice that what we need here is, if we're going to do the trapezoidal rule, and we'll go ahead and skip over the left-hand Riemann sum, we simply need to do the area formula for the trapezoids. And remember, the bases are the outputs, okay? And so you get 150 plus 180, you average the bases, and then you multiply it by the height, 40. And then you're going to go ahead and average these bases, and you're going to multiply it by the height, 30. And then you're going to average these bases, and you're going to multiply it by the height. And then you're going to average these bases, and you're going to multiply it by the height. And of course, I mean, you can go through and clean this up a little bit. This winds up being 20. This is times 15. This is times 10. And of course, this is times 5. It's not like you're going to run into any fractions. Okay? But you would basically, if you don't have the uniform width, the formula only works if you can factor out the delta x, right? That's why the delta x over 2 is sitting out in front in the formula. And you can only factor the delta x out if the delta x is common, if it is a constant for all of the intervals. In this case, it is not. And therefore you have to go ahead and do a little bit more work in terms of using the formula for trapezoidal area. So you have 150 plus 180 times 20 plus 180 plus 195 times 15 plus 195 plus 184 times 10 plus 184 plus, sorry, got to put in parentheses, 184 plus 172 times 5. And you get 17,795. I hope that makes sense. Okay, let's go ahead and do one last example using the tables. And I'm belaboring the point because the tables actually do wind up being used. Gosh, I can't remember the last time there was an AP exam where one of the problems wasn't a tabular problem. And if there's a tabular problem, then the possibility of them actually asking you to use the table to get some sort of approximate area is usually pretty good. Okay, I don't have the actual stats on that, but this is one of those things that it's worth, I mean, it's not really all that complicated, but it's worth slowing down and really nailing it because the odds of it actually showing up are actually pretty good. Now, it's not going to be an exorbitant amount of points. On a 9-point free response question, I can only imagine that it would probably be 1 point, but still, every point matters when you're trying to, not have to take calculus again in college. Okay, and here, this one's a little bit different just because we're actually given a context. Remember how I told you that you're given data when it comes from sort of a scientific, data gathering sort of experiment, whatever scenario. Here, a radar gun was used to record the speed of a runner during the first 5 seconds of a race. See the table below. Using the trapezoidal rule with 5 equal subintervals to estimate the distance covered by the runner during those 5 seconds. Now remember, if you integrate velocity, you get displacement. And since all the trapezoidal rule is doing is giving you a way of estimating the integral, it's giving you a way of estimating displacement. Okay? Because if I were to go from 0 to 5 of v of t dt, that would give me s of 5 and s of 0. Where are you after 5 seconds of running minus where you started? Okay? So this, of course, tells you how far you've run in those 5 seconds. And all you're doing with the trapezoidal rule is you're just figuring out a way to approximate it. This is what it's equal to. We'll figure out what it's approximate to. Now, what is my delta x? Well, my delta x is 1. Like each one of these intervals is a second, right? 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Delta x over 2 is 1/2. And then I'm just going to use the outputs with respect to my formula for trapezoidal rule. 0 plus 2 times 7.34 plus 2 times 9.73 plus 2 times 10.51 plus 2 times 10.76 plus 10.81. Okay, well, let's go ahead and actually do a little bit of work in the calculator. How about 2 times 7.34, that should be a point, 0.34, plus 2 times 9 point, I did it again, 0.73, plus 2 times 10.51, got it that time, 10.76, and that's plus 10.81. Now we still haven't multiplied by delta x over 2, so we do that and we divide by 2. And our answer is he has, or she has, did it say the, I don't know, whoever, the runner has gone approximately 43 meters in the first 5 seconds of running. Okay. That's pretty much the trapezoidal rule. The only thing that might get a little disgusting is it might be a little more complicated function than the ones that I did in the last video, or the numbers in the table that are given to you might be a little bit nastier. But beyond that, I can't see how trapezoidal rule will be that big of a hindrance. But of course, it like I said, it kind of was a good idea to at least stop and do 2 videos on it and make sure we have it under our belt, both doing it with a function and, of course, in this video, doing it with a table of values. Coming up after this will be the videos on improper integrals. Okay, so be looking for those. And as always, email me with any questions that you might have. Bye.